Okay, so we were talking about rotational motion. Rotational motion is a motion where objects spin about some axis, some fixed axis, like here in this fan or this wind turbine. The blades rotate about this fixed axis. Okay, that's the rotational motion. So when objects rotate about some fixed axis, we can explain or describe the motion with some physical quantities, just like we used some physical quantities to explain a linear motion before. So here in the rotational motion also, we can use some physical quantities to explain how fast it is moving, where it is, whether it's accelerating or not, all those kinds of things. Okay, how many times it rotates every second. So the first quantity that we use to explain or to describe rotational motion is angular position. Angular position is where the object is with respect to the angle, okay, with respect to some reference line. So we use angle theta from this positive x-axis to describe the position of the object. So for example, in this case, this particle is at angle theta from this x-axis. Okay? So theta is angular position of that object. And then we use the signs to describe which way the object is moving. Okay, if the object is moving clockwise, then we use negative sign for the angle. If the object is moving counterclockwise, then we use positive sign for the angle. Just like in linear motion, moving to the right is positive and moving to the left is negative. So here in rotational motion, if an object is moving counterclockwise, we consider that to be positive. If it is clockwise, it's considered to be negative. Okay? And the unit for angle is radian. Like I mentioned last time, if you have angle only without any function like sine, cosine, then the unit for that angle is radian. It's very important, not degrees. Degrees is only when you're using sine theta or cosine theta or tan theta. Okay, here these are in degrees. But here, since there is no sine, cosine, only angle, so this one is expressed in radians. And also, we can explain or describe the position of the particle by using the arc length. You can say from the x-axis, how far is that particle? Okay, you can use this s to explain that, to describe that. So this particle is, let's say, 10 centimeters from the x-axis. So there are two ways to point out where this object is. One is using this angle. You can say this particle is 2 pi over 6 radian from this point, or you can also say it's 10 centimeters from that point. Okay, so there are two ways. So, and we know from trigonometry the relationship between the angle and the arc length. So if you have some kind of arc, say that s, and then theta, and then let's say the radius here is r, then the relationship between theta and s is theta is equal to s over r. Okay, that's from trigonometry. Or you can rearrange that to write the arc length as r times theta. You might have seen this in trigonometry before. And when we talk about rotational motion, we often use the term revolution. Okay? Revolution is you start from a point, okay, and then it rotates around some fixed point in a circular path, and then it comes back to the same point. So that's one revolution. Okay. And we know the angle covered in one full revolution is 360 degrees or 2 pi. Okay. In terms of radian, it's 2 pi radian. So starting from here, from this line, it revolves around this point and then comes back. So it makes 2 pi radian angle. Okay, so a little bit of review from linear motion. In linear motion, we know larger the velocity, greater is the displacement. So in this example, so here the one on the left side has lower speed or lower velocity than this one. That's why you have smaller displacement in this case than in this case. Okay, this one is at larger velocity. So that means there is greater displacement. Every second it covers that much distance or displacement, whereas in this case every second it covers that much only. So greater displacement due to greater velocity or larger velocity. So let me ask you this question. So in the picture you have two blocks, one on the top and one on the bottom, and each block is moving along this number line, and you can see the times near the blocks. So this 1, 2, 3, 4, 5, those are the times, okay? The position of the block at different times. So the question is, do the blocks ever have the same speed? So here, this distance is the distance traveled in 1 second time. This distance is the distance traveled in 1 second time. Okay? That distance is the distance traveled in 1 second time. So we need to decide whether they have same speed at any instance, or there is no instance where they have same speed. Okay, so I see an answer says E, and that's the right answer. Yes. So see the distance covered in 1 second time, and if the distance traveled in 1 second time is same, that means the speed is same, because speed by definition, speed is distance over time, and here we are looking at 1 second time. Okay, so we need to see the same distance travel in same time interval to have the same speed, and between 3 and 4 seconds, so this interval, during this interval they travel same amount of distance. That's why the speed is same. If you look at other intervals like 5 and 6, this one has greater speed than that one because it travels more distance. Like from 6 to 7, there is more distance for this one compared to this one. So this one has greater speed. If you look at 1 and 2, this one has greater distance compared to that, so this one has greater speed. Only between 3 and 4, they have the same distance for the same time. That's where they have the same speed. Okay, let's look at this one. So it's asking the acceleration of the blocks are related as follows. So it's asking about the acceleration. Acceleration of A is greater than acceleration of B. Acceleration of A is equal to acceleration of B. Both accelerations are greater than 0. Acceleration of B is greater than acceleration of A. Acceleration of A equals to acceleration of B. Both acceleration are 0. Not enough information is given to answer the question. So it's all about acceleration. So which one has greater acceleration, or they have same acceleration? Okay, so acceleration of B is greater than acceleration of A. Someone is saying that. Acceleration means change in velocity. So change in velocity. Is the velocity changing for A and B? It's constant. Velocity is constant. Yeah, because they cover same distance. So here, this covers this much distance in 1 second, and same distance in this interval also. Same distance in this interval, same distance in this interval. So it travels same distance in same time interval. So that means velocity is constant. If velocity is constant, that means there is no acceleration. Okay. Same thing down here. So same interval in 1 second. For every interval, it covers same distance. That means velocity is constant. If velocity is constant, that means no acceleration. Okay. So both cases, acceleration is 0. So yeah, acceleration of A and B are both 0, which is D. Okay, so just like we saw that how to find the speed in linear part, we can also find the speed in rotational motion. But in rotational motion, instead of calling it just the velocity, we call it angular velocity. Okay, it is denoted by this Greek letter omega, small omega. So angular velocity tells us how fast this object is rotating about this fixed point. So if you look at these two pictures, which one has greater angular velocity? Which one is covering more distance or more displacement, more angle? Yeah, this one is covering more angle in same time. In 5 seconds, it covers 180 degrees or 2 pi, not 2 pi, pi. Okay, so starting from here, it reaches here in 5 seconds. So pi radian is covered in 5 seconds. So that's the angular velocity. In this case, it covers only pi over 4, 90 degrees in 5 second time. Okay, so here it's pi over 10 radian per second. So that means the right one is traveling faster, or it has greater angular velocity. So angular velocity is just like in linear velocity. Linear velocity is change in position over change in time, or displacement over time. So in case of angular velocity, it's delta theta over delta t, okay? Or angular displacement over time. And if W is constant, then the motion is uniform motion. Okay? So it's called uniform circular motion if W is constant, if the angular velocity is constant. So I just showed you this previously. So to find the angular velocities, angular velocity is delta theta over delta t, how much angle it covers in given time. So angle covered here is pi over 4. Is that pi over 4? No, not pi over 4. That's this whole thing is 2 pi, half is pi, That means pi over 2. Sorry, 90 degrees is pi over 2. My mistake. So on the previous one, that should be pi over 2. Okay, 90 degrees is pi over 2. Yeah, so pi over 10. So pi over 2 over time is 5 seconds. So that's pi over 10. And the unit for omega is radian per second. In case of linear motion, it's meters per second, but here it's radian per second. So here, omega is delta theta. Delta theta is from here to here. It covers 180 degrees, which is in terms of radian pi. And then time is 5 seconds. So that's pi over 5 radian per second. Okay. So that means this is faster. Sometimes we also use the term period to explain the rotational motion. So period is how much time it takes to make one complete revolution. So starting from here, it revolves around this and then back again to the same point. So what's the time for one complete revolution? That is denoted by this capital T, which is time period. Unfortunately, we don't have different symbols for time period, symbol for time period. We are using the same symbol for tension and time period. If you talk about heat, we use T for temperature. Okay. So physics has some limitations with the symbols. Sometimes it uses same symbol for different physical quantities. So angular velocity or angular speed is related to time period by this formula. So omega is equal to 2 pi over t. And often we use a term called frequency to explain rotational motion. Frequency is how many revolutions it makes in 1 second time. Okay, that's the frequency. So let's say starts from here. Okay, it makes like 100 revolutions in 1 second. That's the frequency. I mean 100 revolution. So number of revolutions per second. And this frequency and angular velocity are related by this formula. Okay. So angular velocity is equal to 2 pi times frequency, whereas angular velocity is in terms of period, it's 2 pi over time period. Okay, so let's look at how to use the formula. So a ball rolls around a circular track with an angular velocity of 4 pi radian per second. So you have a ball, it's revolving around some fixed axis, and its angular velocity is 4 pi radian per second. So what's the period? So we have the formula for relationship between omega and time period is 2 pi over t. So t is 2 pi over omega. 2 pi omega is 4 pi. So pi and pi cancel. So 1 over 2. Time period has the unit of seconds. Okay. Okay, so next thing is we are given RPM frequency So revolution per minute or rotations per minute is frequency, 6,000 over pi RPM. With that, we want to find omega. Okay. So you can use formula, or you can just use basic arithmetic here. So the unit of omega is radian per second. So we want to convert this to radian per second. If you do that, then that gives you the omega. But if you want, you can also use formula. Okay? Formula is omega is 2 pi f. Now let's do without using formula. So 6,000 over pi revolution per minute. So we want to convert this revolution per minute to radian per second. Okay? So 6,000 over pi. In one revolution, how much angle it covers? One complete revolution, what's the angle covered? 2 pi, yeah. So 2 pi, and in one, so 2 pi radian. And in 1 minute, we have 60 seconds. Okay, now you see we have radian per second, so that's what we want. So now you need to do the math. So 6,000 divided by 60 would be 100. Pi and pi cancel. So that's 200 radian per second. Okay. And if you want, you can use this formula also, but still you need to convert that to radian per second, even if you use the formula. Okay, so there is a relationship between angular speed and linear speed. So angular speed is delta theta over delta t. Okay, how fast the object changes the angle. So that's the angular speed, whereas this linear speed is delta x over delta t. Okay, in this case, it's delta s over delta t. Like if I mentioned in the very beginning, there are two ways you can explain the motion of this particle, one using this angle, the other one using this s. Okay? In terms of angle, how fast it is changing the angle, we use this omega. In terms of s, how fast it is changing its arc length, that would be this v. Okay? And there is a relationship between, just like there is a relationship between theta and s, so s is r theta. Likewise, we have a relationship between v and omega. So v is omega times r, or r times omega. Okay. So this is how fast it changes the arc length. Okay, so let's look at the worksheet problem 2 from worksheet 18. On number 2, it says there is a solid disk rotating so there is a solid disk, just like the one we used in lab last time, and it's rotating at 900 RPM in the beginning. So That's omega 1 or omega I. And it slows down uniformly to 300 RPM. So our W final would be 300 RPM. So the frequency angular velocity decreases from 900 RPM to 300 RPM. While it makes 50 revolutions. Okay, so delta theta, during this slowing down of angular velocity from 900 to 300, it makes the angular displacement of 50 revolutions. So we want to find angular acceleration. Angular acceleration is what? And time for this to cover that many revolutions is what? So given omega I is 900 RPM, omega F is 300 RPM. And delta theta is 50 revolutions. So how do we find alpha? So we have three formulas. If you remember from linear motion, we have delta x is equal to v final squared minus v initial squared over 2a. Delta x is equal to v initial t plus 1/2 at squared, and then a is equal to v final minus v initial over t. Okay, so we have the angular counterpart of these three equations. The angular counterpart is x is denoted by theta, so delta theta is, and v is denoted by omega, omega final squared minus omega initial squared, and a is denoted by alpha in case of rotation. So we can have delta theta is equal to omega I t plus 1/2, a is alpha, time is t. Time for both linear and angular motion are same. Okay. And then this one, a is alpha, v is omega, vi is omega I, and time is time. So we need to decide which formula we want to use to get alpha. We don't have t, so we cannot use the third one. First one, we have theta, and we have omega, f and omega I, so that means we can use this one. So let's use the first one. So delta theta is omega final minus omega initial squared over 2 alpha. And here we want to find alpha, so you can rearrange the equation. Alpha is equal to wf squared minus wi squared over 2 delta theta. Okay, so plug in the numbers. So alpha, if you remember from the lab, has the unit of radian per second squared. Okay, that's the unit. So here we have the unit in RPM, revolutions per minute. So somehow we need to convert this into radian and second. Okay, that's the first thing we need to do. So let's convert this into radian and second. So 900 revolution. In one revolution, there is 2 pi radian, and in 1 minute, per minute means over a minute, in 1 minute we have 60 seconds. Okay, so that will give us omega I, which would be 30 pi radian per second. Likewise, we can convert this into radian per second. So 300 revolution, in one revolution we have 2 pi radian, and in 1 second, or sorry, 1 minute we have 60 seconds. So if you do that calculation, you get 10 pi radian per second. Okay, that's omega f. Same thing we can do with delta theta. So delta theta is 50 times in 1 revolution, there is 2 pi radian. So that is 100 pi radian. Okay, so we want to convert everything to radian and second. So now let's plug in the numbers. So Wf or omega f 10 pi squared, Wi 30 pi squared, to delta theta is 100 pi. Okay, so that will be our alpha. So alpha is 4 radian per second squared. And this negative, there's a negative sign here. This negative sign implies that it's slowing. Now the next thing is we want to find delta t. So again, look at the 3 formulas and see which one you want to use. So we have now alpha, we have Wf, Wi, so that means we can use this third one. So rearrange this equation in terms of t. T would be omega final minus omega initial over alpha. Omega final 10 pi, omega initial 30 pi, and alpha is negative 4. So that will give you 5 seconds. You got 12.6. Let's see, 2 theta. Maybe I didn't do the math correctly. So did you do the square? 10 squared, 10 pi squared, 30 pi squared over 200 pi. Okay, maybe, yeah, okay, my answer may be wrong. I was in hurry this morning, so, okay. So let me make a correction here. So that's negative 12 you got. Okay. Okay. So that means here also you need to convert, you need to make the correction. So 12. Yeah, I think I forgot to maybe multiply that by pi because there's extra pi on the numerator and maybe I missed it. Okay, so let's look at some more questions. So if you guys remember from linear motion, if you have velocity versus time, okay, so this is the graph of how the velocity is changing with time. If you want to find the displacement, how much displacement the object will make from some time, let's say 2 seconds to 4 seconds. So do you remember how you find the displacement from this VT graph? Yeah, area under the curve. So that's not right. So from here, from 2 seconds to 4 seconds, you see what's the area under the curve. Okay, so that area under the curve gives you the displacement. Likewise, if you have acceleration versus time, and you want to find velocity from some time, let's say 2 seconds to 4 seconds, then the velocity would be area under the curve. Okay? That's one thing. The next thing is, if you have x versus t, and you want to find velocity, then it's the slope of that curve. Okay, slope of this curve gives you the velocity. So to get displacement, you need to find the area under VT curve, but to get velocity, you need to get the slope of xt graph. So let me just put a small chart here so that you don't forget. So given xt graph, to find v, you need to find slope. Okay. Like if you are given VT graph and then you want to find the acceleration, you need to find the slope of VT graph. Okay, here xt graph. And then if you are given VT graph and you want to find displacement, okay, to find delta x, then you need area under the curve. Likewise, if you are given AT graph and then you want to find change in velocity, okay, you need area under the curve of AT graph. Here it's VT graph. Okay. So these are the rules for finding different quantities from different kinds of graphs. So let's look at a question. Okay. So here we have omega versus time. Omega is similar to the velocity. Okay. Velocity versus time. And we want to find how many revolutions. Revolution is just like displacement. So what's the displacement? So if you look at the rule there, to find the displacement from velocity versus time, you need area under the curve. So you want to find area from starting point to 4 seconds. That will give you displacement delta theta in terms of revolution. So let's count that. So that's 1, that's 2 revolutions, 3 revolutions, 4 revolutions, 5, half and half is 1, so that's total is 6 revolutions. Now here the unit is revolution per second, but for some reason, if we have like here, let's say radian per second, then this area would be in unit of radian. Okay, if you have radian per second here, then this would be 1 radian, this would be another radian, this would be another radian. Okay, so your unit depends on how this omega is expressed. Since here we are using revolution per second, so these are the revolutions. Okay. So let's look at this question. Starting from rest, a wheel, oops, what happened? A wheel with constant angular acceleration turns through an angle of 25 radian in a time t. Through what angle will it have turned after time 2t? So you think it's doubled? It's constant angular acceleration, yeah. So you can do like a basic math here. So starting from rest means omega I is 0. And then theta is that. And angular acceleration is alpha. So delta theta is, you need to use one of the formulas there. So which formula should we use? Delta theta has two formulas. So one is Vi omega I t plus 1/2 alpha t squared. So this is 0. Initial velocity is 0. So 1/2 alpha t squared. You can use that. So for t, delta theta would be 1/2, let's call that 1 alpha t1 squared. And then for 2t, that's just t. For 2t, delta theta 2 would be 1/2. Alpha is same, okay, constant. But here now t is 2t, okay, 2t squared. So we want to find this. So let's divide this equation by this equation, or 2 by 1. 2 divided by 1. So delta theta 2 over delta theta 1 is equal to 1/2 alpha 2t squared is 4t squared over 1/2 alpha t squared. Okay, I'm just dividing this thing by that. So 1/2 and 1/2 cancel, alpha and alpha cancel, t squared and t squared cancel. So delta theta 2 over delta theta 1 is 25 radian is equal to 4. So that means delta theta 2 is 2 times 4 is 8. 20, this is 25, not 5, 2. 25 times 4 is 100 radian. So because we have this t squared in this formula, so that means it's not actually double. Doubling this doesn't double that. It will quadruple that because of this squared. Double t means you are quadrupling this delta theta. So let's see. So in this chapter, we'll be talking about rotational objects, not rotational, rigid objects. Rigid objects are those objects in which the particles that make up the body object does not change its position. Okay, they remain fixed at their location. So in rigid bodies, we consider that the particles that make up the object remain fixed. They do not change the position. And here we will be talking about the combination of translational motion and rotational motion. So translational motion is you have a particle here, it's moving forward like that. Okay, so from 1 to, let's say, here. And rotational motion is it's rotating about some fixed axis. So this is the axis, it's rotating like that. And here we will be talking about combination of these two. So here, if you see this motion, it's moving this way, forward direction, as well as it's rotating. So you see here, this particle is rotating above that fixed point. It's rotating. Do you see that? It's rotating. If you focus at this point, it's here now, it's here, it's rotating. So there is both rotation and translation in this motion. And that's what we are going to focus in the next part. So when an object is rotating about some fixed axis, we know it's described by theta or omega. And omega is basically how much angle it covers in a unit second time. Okay? And if we consider a rigid body like this one, it is made up of zillions of particles. And for each and every particles in this rigid body, this omega would be same. Okay? If this particle has omega of 2 radian per second, then this will also have the same omega. Okay? Each and every particle in this object will have the same angular velocity because they move at the same time. Okay? That's why they cover the same angle in same time. So they have same angular velocity. That's a very important thing that you need to keep in mind. So let's say you have this question. Rashid and Sophia are riding a merry-go-round that is spinning steadily. Sophia is twice far from the axis as is Rashid. Sophia's angular velocity is half that of Rashid, same as that of Rashid, twice, 4 times. We cannot say without knowing their radii. So what's the answer? It's same, yeah. Twice, I don't know why. I just mentioned that for each and every particle on this object, they are moving at the same rate. Okay? They are moving at the same rate because they do not displace from their position. So omega for each and every particle would be same omega. So that means R and S will have same omega. Okay, that's right. So B is the right answer.
Where it's different with torque.
What's that?
Where it's different with torque.
Different with torque?
Where like if you're doing with the torque, R would be.
Yeah, right. Yeah. So if you consider the torque at different points, it would be different because torque depends on the distance. Yeah. Same thing with the velocity. Okay, so we know we have 2 types of velocities. One is omega, angular velocity, and this linear velocity. And this linear velocity is R times omega. Although omega is same for each and every point, but this velocity depends on R. Okay, how far the point is. So R and S will have different linear velocities, although they have same angular velocities. So if they have same angular velocity, then what would be the, so Sophia is twice as far from the axis as is Rashid. So Sophia's speed is half that of Rashid, same as that of Rashid, twice, 4 times. So again, this V is how much arc it covers in certain time period. So definitely this covers more arc in the same time compared to this one. This covers bigger arc. So this one has greater linear velocity than this one. So V is omega R, and R for S is twice as that of, R for S is twice as that of R. I'm mixing the r and r. The radius for S is twice as that of this r. So that means S velocity would be that half or twice. Twice as much arc or distance covered in same time. Okay. So that means V for point S would be twice as much as V for R. Okay, I think we are out of time. We'll just end it here. We'll discontinue the discussion next time. There is a quiz on Blackboard, so please do not forget to complete the quiz. If you haven't signed up for the meeting, please do that to talk about your overall standing in this course and to talk about the test.